Okay, silly people, here's the situation. Uh, we are meant to find uh, this spin angular function, 0, 1/2, 1/2, and then we're meant to do this operator of the polyvector times the position operator onto the spin angular function in order to find what's going on with it. So this problem has a little bit of plug and chug. I've already written down the general equation for a spin angular function. That's the fancy y equation there. So I'm just going to plug in these values for fancy y, 0, 1/2, 1/2. L is 1/2. Um, J is L, no, L is 0. J is L plus 1/2. So we're going to be using all the pluses in this equation as M is 1/2. The normalization constant out front is just 1 over root 1. We have a plus 0 plus 1/2 plus 1/2. Y 0, 0. And then we have a square root 0 minus 1/2 plus 1/2. Y 0, 1. But minus 1/2 plus 1/2 is 0, so the second um, component of this function is just 0, and so we just have y 0, 0 and 0 for the components of the function. Now we should operate on it. Oh no, first let's just talk about that y there. That's a spherical harmonic. Y 0, 0 is actually a constant. It's just 1 over root 4 pi. Now let's do the operator. So sigma dot x will form a matrix which will look like z minus z, x minus I, y, and x plus I, y. When we operate on this vector, will just give us 1 over root 4 pi z and x plus iy are the components. This problem is in the geometry of a sphere, so I think it'd be better if we converted to spherical coordinates using the regular old spherical coordinate transformations: r sine theta cosine phi, r sine theta sine phi, and r cos theta. Just plugging those guys in there. We have 1 over root 4 pi, take the r out already, cosine theta, and both of these are a function of sine theta. We have cosine phi plus I sine phi, and that's just Euler's identity, which we can write this now as cos theta over e to the I phi sine theta. And what we want to do is we want to put this angular function that's been operated on in terms of another angular function. How are we going to go about doing that? Well, look back at the general equation for an angular function, which I'm going to grab and copy down. We're going to want our spherical harmonics in the components to match. That's going to be the game. So we better convert this guy into spherical harmonics. which spherical harmonics looks like cosine theta, I'm looking at y10, which is given by 3 over pi under a square root times cosine theta. And then what looks like e to the I phi sine theta, that looks like to me y11, which is given by 1, or no, it looks like negative 3 over 8 pi e to the I phi sine theta. All right. So let's just solve for cosine theta on both of these guys. So I'm gonna do 4 pi over 3 y10 is equal to cosine theta, and we'll have minus 8 pi over 3 y11 is equal to e to the I phi sine theta. And then just plug those bad boys into our equation. Sigma dot x of fancy y. Shoo. I'm bad at the fancy y. Shoo. It was 1 over root 4 pi, or r, or root 4 pi, and it's going to be something big now. We've got root 4 pi over 3 y10, and minus root 8 pi over 3 y11. We'll factor out a root 4 pi from both, and that'll cancel out the denominator in front. And we'll also factor out of 1 over root 3, which will leave us with r over root 3 r over root 3 will have y10 and minus root 2 y11. Okay. Now, looking at the general function for the spin angular function, we know now that L is going to end up being equal to 1 for this guy. We have a minus sign in the vector, so we're going to use j is equal to L minus 1/2, so j is equal to 1/2. And m has to be 1/2, because 1/2 minus 1/2 is 0 up top. Okay. Now plugging in all of that stuff, the normalization constant out front is going to be 1 over root 3. That's nice. We'll have minus, what is this? 1 minus 1/2 plus 1/2. So it's root 1 times y10. And then down bottom we'll have 1 plus 1/2 plus 1/2 y11. Alright, so the normalization up top is 1. I'm going to factor out a minus sign as well to bring the minus sign down bottom. So we have y10 and minus 2, no, minus root 2 y11. Notice now that if we just multiply this bad boy by r, we get the same result as up here. Or we multiply it by minus r, and then it all checks out. Okay. In writing, this stuff is equal to minus r times this stuff. All right, what does that mean physically? Well, if we take a look at this operator, what is it doing? It's a spin operator multiplied by a position operator, which when it is in a combination like that, it can do multiple things. It can translate, it can scale, it can even change the parity of a angular function. In this case, it scaled it and changed the parity. So that tracks. It didn't translate it at all. If there was a change in J or M, that would actually indicate that would end up translating into a translation space. But just the only thing that changed here is L. So all we did was scale it and flip it. All right.